Right now, bolted to a wall in your basement or tucked into a cupboard somewhere in your house, there is a machine that has not fundamentally changed in over a century. It burns gas or runs electricity through a coil to heat water, and it does that job the same way water heaters have done it since the 1890s. It is loud when it kicks on. It wastes a huge amount of energy heating water you will not use for hours. And it has a hard ceiling on how hot it can actually get, which is exactly why hospitals, chemical plants, and heavy factories still rely on enormous, expensive, energy-hungry boiler systems for anything above a certain temperature. But in a laboratory in China, a team of scientists has built something that does not use a flame, does not use a heating element, and does not have a single moving part in the traditional sense. It uses sound. Loud, precisely tuned sound, bouncing back and forth inside a sealed tube to pump heat to temperatures that would make a normal water heater catch fire. If this technology scales the way its inventors believe it can, the water heater sitting in your house right now could look as primitive in 20 years as a wood-burning stove looks today. This is not science fiction. It is a real, published, peer-reviewed breakthrough that could change how we heat water, how heavy industry generates process heat, and how much carbon the world's factories put into the atmosphere every single year. If you are enjoying videos like this, please hit the like button, because it takes a lot of effort to make these, and subscribe so you do not miss the next one. The idea behind this invention sounds almost too simple to be real, but it took nearly a century of physics to get from the basic principle to a working machine. To understand why it matters, you first need to understand what is actually happening inside the water heater in your home right now. Almost every water heater on the planet, whether it burns gas or runs on electricity, works by transferring heat directly into water through a heating element or a flame. It is a brute force method. You are essentially throwing energy at water until it gets hot, and a huge amount of that energy escapes as waste heat along the way. Heat pump water heaters, which have become more popular in the last decade, are smarter. Instead of generating heat directly, they move existing heat from the air around the unit into the water, the same basic principle an air conditioner uses in reverse. That is a real improvement in efficiency, and Chinese manufacturers have been aggressively expanding this technology, with the domestic heat pump water heater market in China valued at well over $3.5 billion in 2025 alone, and growing at nearly 12% a year. But even the best heat pump systems have a temperature ceiling. Standard heat pumps struggle to push water much above the mid-50s in Celsius terms, which is fine for a shower, but useless for the kind of high-temperature industrial processes that petrochemical plants, metal refineries, and ceramics manufacturers depend on every single day. Those industries still burn enormous quantities of fossil fuel just to generate heat above 300 degrees Celsius, because nothing efficient existed that could reach those temperatures without combustion. That is the gap a team at the Chinese Academy of Sciences set out to close, and the tool they used to close it was sound. The technology is called a thermoacoustic Stirling heat pump, and the physics behind it goes back to a completely different invention from 2 centuries ago. In 1816, a Scottish engineer named Robert Stirling designed an engine that used the expansion and contraction of a sealed gas to produce mechanical motion, without any combustion happening inside the engine itself. It was elegant, efficient, and largely forgotten once internal combustion engines took over the industrial world. But the underlying principle never went away. If you compress a gas, it heats up. If you let that gas expand, it cools down. Stirling built a mechanical engine around that idea using pistons. The Chinese Academy of Sciences team took the same core principle and rebuilt it using sound waves instead of moving pistons. Here is the simplest way to picture what is actually happening inside the device. Imagine a sealed metal tube filled with gas. Now imagine a loudspeaker at one end, blasting an extremely loud, precisely tuned tone into that tube. As the sound wave travels through the gas, it creates rapid pressure changes, compressing and expanding pockets of gas as it moves. Just like Stirling's mechanical piston, compressed gas gets hot, and expanded gas gets cold. The sound wave is doing the same job a piston does, except there is no metal touching metal, no friction, and nothing physically wearing out over time. The research team, led by scientist Luo Erxang, built what they describe as the world's first dual-acting free-piston thermoacoustic Stirling heat pump, and the specific innovation that made it work was something they call reverse phase operation. In simple terms, they found a way to electrically flip the acoustic field inside the system, which lets the hot and cold ends of the machine effectively swap roles. That single trick solved a problem that had kept this entire category of technology stuck in laboratories for years. It allowed the compressor part of the system to keep operating at a comfortable, manageable temperature, even while the output end of the machine reached temperatures that would destroy a conventional compressor almost instantly. And the results genuinely are remarkable. In testing, the prototype took heat starting at around 14 degrees Celsius, roughly the temperature of a cool room, and pumped it all the way up past 270 degrees. In a separate test, the machine raised the temperature from 25 degrees to 166 degrees, and when the researchers pushed the ambient starting temperature up to 67 degrees, the system delivered a heat supply temperature of 214 degrees Celsius. To put that in context, a typical high-end heat pump water heater in your home tops out somewhere around 55 to 65 degrees. This Chinese prototype was hitting temperatures nearly 4 times higher than that, using nothing but sound waves and a sealed gas loop. At its peak efficiency, the system achieved what engineers call a coefficient of performance of 1.68, meaning it delivered substantially more heat energy out than the electrical energy it consumed to run, which is the entire point of a heat pump in the first place. But the real ambition behind this invention is not actually your shower. It is heavy industry. Luo Erchang and his team have been explicit about where they see this technology going next. Petrochemical plants, metal refineries, and ceramics manufacturers all require heat well above 500 degrees Celsius for their core industrial processes, and right now almost all of that heat comes from burning fossil fuels directly, because nothing else could reach those temperatures efficiently. The research team believes their thermoacoustic approach can eventually be scaled to reach between 500 and 800 degrees Celsius, which would allow it to replace the fossil fuel burners that currently sit at the heart of some of the most carbon-intensive manufacturing processes on the planet. If that happens, the impact would dwarf anything that happens in a residential water heater market. We are talking about entire categories of heavy industry potentially switching from combustion-based heating to a completely solid, sound-driven, zero-combustion process. It is important to be honest about where this technology actually sits right now, because that is exactly what separates a real scientific breakthrough from a marketing headline. What the Chinese Academy of Sciences team built is a laboratory prototype. It has been tested, measured, and published in a peer-reviewed journal called Applied Physics Letters, which means other scientists have reviewed the methodology and the results. But it is not sitting on a factory floor generating industrial heat today, and there is no announced commercial timeline for when it might be. Thermoacoustic technology as a category still has real engineering hurdles ahead of it. Building acoustic drivers powerful enough to generate the sound pressures needed at industrial scale is expensive. Manufacturing the precision components required to keep the system sealed and efficient at those extreme temperatures is not trivial. And like every promising laboratory technology before it, the gap between a working prototype and a cost-competitive commercial product is where most breakthroughs actually die. But every major technological shift in industrial heating has started exactly this way. It starts with a small team asking a question nobody else had bothered to ask properly. What if you removed the moving parts entirely? What if sound could do the job that pistons and flames have always done? The work coming out of the Chinese Academy of Sciences did not invent a new law of physics. It found a genuinely clever way to solve an engineering bottleneck that had kept a 200-year-old idea from ever reaching its full potential. And now that the bottleneck is solved, the question is no longer whether this can work. It is how quickly someone can build a version of it cheap enough for a factory floor, and eventually, cheap enough for the wall of your basement. There is something strange about sitting with an idea like this. The water heater humming away in most homes right now runs on essentially the same core principle as machines built well over 100 years ago. And yet a small team of physicists working with sound waves and sealed metal tubes may be quietly building the thing that finally replaces it, not with something loud and flashy, but with something almost silent, built from nothing but precisely tuned pressure waves and a sealed loop of gas. So here is a question for you. Which everyday appliance running in your house right now do you think is next in line to be replaced by something you have never even heard of? Let me know in the comments.